right, everybody. Whoa, slap. We're gonna a couple of minutes behind schedule, so we're gonna get moving. All right, a little loud. All right, sounds good. I talk loud to start with. So, my name is Matt Chartier. I'm the chair of the BSc Geo-Institute. I would just want to thank everyone for coming today. You know, it's been a couple of years since the Geo-Institute had a in-person event, and I'm glad it could be something as special as the Chuck Ladd, memorial lecture. I didn't know Professor Ladd as well as I would like to have had. I was lucky enough to attend or sit in a handful of some of his classes in some of the last years that he taught advanced soil mechanics at MIT. And, that experience definitely left an impression on me. And I can just imagine the influence he had, on many people here that worked more closely with him or had him as an academic advisor. I was just, a couple hours ago having this with somebody else that's sitting here as well, a technical discussion, project related. And we were talking about some soil behavior, a lot of opinions flying back and forth until basically, somebody put up one of his beautifully handwritten MIT class notes up on, and that was it, discussion over. I mean, those notes, I'm sure everyone has an electronic, if not paper copy of them somewhere, and they carry more weight than most textbooks. I think a lot of people would agree. So on behalf of the, BSc, I'd like to welcome Professor Ladd's brother, Richard Ladd. There you are. Thank you. And sister, Amanda Ladd Northrup, welcome and thank you for coming in person. Also want to obviously thank our speaker, Professor Don DeGroot, and all our BSc sponsors. If you don't mind, I don't know who's operating the slides. It's probably me. I'm disorganized as usual, but yeah, there we go. Well, there's 35 sponsors, so I'm not going to read them all off because that would be annoying. But really want on behalf of the BSc thank the sponsors for making this event and everything else BSc does possible. So just a couple of housekeeping items in case of emergency. The fire exits are up there. The bathroom is somewhere out in there, not in here. And other than that, just please turn your cell phones down during the event. I got to do the same as well. But with that said, I'll pass the torch off to Professor Santagata from Purdue University. Thanks a lot, everybody.
So thank you. Good evening. So I'm going to, oopsie. Sorry. Good evening. I'm going to first start with acknowledging the donors to the Chuck Ladd Memorial Fund that make this lecture possible. The endowment was created in 2014 and 2015. The slide acknowledges both the seed donors and the many other generous donors that have joined forces since then. And I would encourage you to think about contributing to this fund, which is intended to provide this opportunity to professionals and students to listen to great speakers talking about soft soils in perpetuity. And we're actually lucky that this year, thanks to the generosity of Northeastern University, the organizers did not have to actually dip into the original funds. So that's good news, and we can continue growing it and making sure it endures. If you need any extra incentive to contribute to the fund, I'm going to tell you that as a donor, you're going to be gifted a wonderful version, not new, a second and improved version of the Chuck Ladd mug that many of us still have from the Ladd Symposium in 2001. So before passing on the microphone to Professor Sheehan to introduce the Ladd lecture, I would like to say a few words about Professor Ladd. Many of you are very familiar with his accomplishments, both as a researcher and a practitioner. And I'm not going to go there. I'm actually going to take a little bit of a different take on this. And I want to share a few memories related to Professor Ladd as my advisor and my teacher. So I met Professor Ladd in 1991 when I first moved to Boston for graduate school. I was a student in 1361 and in 1322 during my first year. He was my academic advisor for many years. And then in the second part of my PhD, he joined Dr. G as my PhD thesis advisor. And actually, oh, I forgot to say this. Now I'm going to get scolded. So let me back off a second. I'll remind you of another very important initiative related to Professor Ladd, and that's hosted at Tufts, and that's the Charles Ladd Digital Library. That is a collection of his research reports, his notes, his publications, and his thesis links. And it's going to be a wonderful resources for all of us who work in the area of clays, for sure. So sorry for that hiccup. Anyhow, so as I said, he was my PhD advisor, and the picture that you see there is actually the day him and Dr. Germain signed my PhD thesis, and sort of that was the bookend of my long adventure at MIT. Chuck was a great professor. He was truly a master in preparing and delivering fantastic lectures. He was a supportive advisor, a tireless reviewer of paper and chapter drafts. And he was an even better friend. Once I left at MIT, I found I had a real friend who cared about me and my life, and it was just incredibly generous. And this is actually the copy of the Terzaghi lecture he gave to me when I finally left MIT to go to Purdue. So interestingly, when I got to Purdue, I was assigned a lab space that on two of the walls had a gallery of pictures from famous geotechnical engineers who had visited and researchers who had visited to give talks. And sure enough, when I got there, staring at me above the CRS, he would have liked that, the continuous compression curve and all of that was Chuck Ladd. And what you're seeing up there is the circa, I think 1984 was written on the back, and a much younger and just super handsome version of Chuck, not the Chuck I knew from a few years. I mean, it's not that he wasn't handsome. It was just that it was a different age. That's you misunderstood me. Okay. And so, as many of you know, Chuck was an incredibly gifted teacher whose knowledge impacted generations of MIT students, and whose teaching style inspired many of us. I mean, most of us who ended up in the business. And he was quite aware of this impact. In 2012, Chuck was interviewed as part of the lessons learned from the GeoLegends. This is done by GeoStrata and graduate students from the GIGSO, Geo-Institute, graduate student organizations across the country run these interviews. And actually, I love the fact that he was interviewed by one of my PhD students who was working on soft carbonatic clays, Alain Helhoayek. And it was actually kind of cute. I went back to an email exchange between Alain and Chuck, and truth to what Chuck was about. After the interview that occurred in Concord, the evening ended with a lobster dinner and cocktails at a nearby restaurant. And I say truth to what the person Chuck was, is because, yes, he was laser focused on work, but he was very generous with students, and there was always an opportunity and a time for a good meal, a good drink, and good company. That was always something he profoundly cared about. So in the interview, Alain asks him, what do you consider your most significant contribution to the geotechnical engineering profession? And Chuck says, and I'm going to just reword a little bit. He says, well, despite the, certainly papers like the SHANSEP paper, the Terzaghi lecture have had a great impact on the geotechnical profession, but based on the feedback that I've had from students regarding the impact that my class has had on their knowledge of soil behavior and soil mechanics, on their ability to tackle problems in a structured way, and on their attention to details that I've instilled in them, I have to say that my teaching has been the most significant contribution to the geotechnical engineering profession. I think I would probably agree. That's last thing he says, attention to detail. Anybody who has worked with him knows that was so core to everything he does, to what he was as a teacher, to what he was as a thesis advisor, and certainly I can only imagine to his success as a practitioner, as a consultant. And so I thought I would give you a couple of examples, right? The attention to detail. This is a picture from his notes that shows the variation of the peak friction angle, the function of confining stress for sands. And it's a classic Ladd style drawing. And and you know, it shows you the importance of everything, the importance of the words, the importance of the graphs, the importance of the symbols, okay? The importance of the symbols. Symbols matter. And so what you're seeing here is data from different sources. The higher relative density, of course, they have to be shown with a darker symbol, right? More solids. And Ottawa sand is shown with a circle, of course. It's a rounded particle. And then the Sacramento River, well, that's subangular, so a square. And Chattahoochee River sand, well, that has to be an hexagon because it contains mica, and that echoes the crystal structure, right, of mica. And you have to know that if you work with him, none of this was by chance. It was all by design, right? I think this is a good illustration of that. So his attention to details extended. Well, actually, let me say one more thing. Sticking with symbols, okay? Every Christmas, Chuck would share in the last years a Christmas letter, right? And this is the 2011. It was perfectly structured, as you would expect. There was the work section, and then the family section, and then whatever other section, you know, was part of the narrative that particular year. And with, you know, detailed news about his family, about the family events, his professional life, and the projects and the soils involved. And in 2011, the soil he was working was a thick and soft silty clay from a tidal marsh core area of the Hudson River. I mean, who talks about these things in their Christmas letter? Okay, this was a bit of what Chuck was about. But the reason I actually pulled out this Christmas letter from 2011 is because it was accompanied, as was normal, by a family picture on some nice vacation he and his wonderful, very big family had gone to. And the pictures typically came with a legend. And you know, with a legend and really carefully chosen symbols. As you see here, a square for CCL, hexagons face down for his kids, hexagons point up for the spouses of his kids, circles for grandkids and great-grandkids. And I was surprised because that he did not distinguish between those two generations. And the diamonds for those who had not yet joined the family in official terms, right? But this is sort of just quintessential, just Chuck, the attention of details. And then the same attention of details went to the degree to which he reviewed our papers and our chapters. And here, I'm a bit of a romantic. I've kept everything. So I've kept every chapter and every paper that Chuck and Dr. Germain have edited. And so these were Chuck's comments. You know, I think Don once said pages and pages, more pages than you gave him came back, right? Comments about the first chapter that we wrote on the small strain stiffness. And detailed comments on how to best articulate arguments, how to choose the best data, how to illustrate the points that to make, and how to use the right words, because words mattered. And saying the data showed was different from saying the data suggested, was different from saying the data indicated, and was different from saying the data demonstrated. And he was adamant about these nuances in the way we delivered what we had learned. And then, of course, at the top, always CCL and the date. You would not need ever want to forget that when you give him something, right? Initials and date. Finally, I think the last key piece that was so critical to making Chuck just a fantastic teacher was, you know, he was truly an engineer, was his ability to feed directly his work as a consultant into the classroom. I did not have the slide today. I called my husband. I asked him to look through his 1322 notes and pull out his final. And he remind me to tell you, he got an A+ on this exam, by the way. He emphasized that I should bring this up. But you see, these were just, I grabbed a few questions, you know, response of a breakwater in Holland, surcharge design for bridge abutments fills in Brazil, settlement of peat for road in Nigeria, cut slope failure in stiff CH clay in Thailand. This is how he fed his profession into the classroom. So, I would like simply to end with a picture of some of his students. This is just a few of us gathered for the CCL symposium in 2001. There's many more out there, hopefully online and here. And just as a reminder that Chuck's teachings continue to live through us and our students and the many professionals out in the world. And I thank you for the opportunity to talk. I thank the organizing committee for the opportunity to say a few words about Chuck and to be part of this program. Thank you. Now, I would like to introduce Professor Tom Sheehan, Professor of Civil and Environmental Engineering and Executive Vice Provost for Northeastern, who's going to introduce our lab lecture. Thank you, Tom.
Thank you, Marika.
Good evening, everyone. And what a great memory and introduction of Chuck to the group. I want to go ahead and welcome all of you to Northeastern. So wearing that hat, and obviously to the fourth Charles Ladd Memorial Lecture. As Matt said, it's wonderful to be back again with people, to see colleagues and students and other guests. And I especially want to welcome, as Matt did, members of Chuck's family who are here. And in particular, I want to recognize Richard Ladd, his brother, who is also a Northeastern alumnus. So I'm always biased to Richard. So welcome, Richard. I will say that one upside of COVID is that we all got used to coming into events like this via Zoom. And in fact, we have as many or more registrants via Zoom tonight than we do in person. So I want to welcome people who are here coming in remotely, including, as we know, one of Don's and my classmates who is here who's eating his breakfast in Thailand while watching the lecture tonight, which is really cool that we have people coming from around the world who have come in to hear the lecture. Before I introduce Don, I want to also acknowledge the tremendous work by BSCES, Lucy Jen in particular from our organizing committee, and also my coworker in my office, Molly Liddell, who did a tremendous amount of work to get the reception together and also the logistics for this. So thank you to BSCES, Lucy, and Molly for all your work on that. I have the great honor of introducing one of my best friend and colleague and classmate, Don DeGroot, who is a professor of civil and environmental engineering at the University of Massachusetts Amherst, and he earned his SCD with Chuck in 1989. And while I don't want to disregard all of his professional and academic accomplishments, we can read about those elsewhere. And you can read them off the flyer. So you don't need me to say that. Like Marika, I would rather take it to a more personal level and talk about a couple things that I really think epitomize both Don as a professional and as a person, but also his relationship with Chuck. Really, I want to first talk about the strong bond that Chuck and Don had over the years while Chuck was alive. Starting when Don came to MIT in the mid-1980s until Chuck's passing, they developed a personal and professional relationship that was truly extraordinary. And I know it was special to both of them. Don has continued Chuck's legacy in an exemplary manner in a lot of ways, both as a geotechnical engineering professional and researcher, a gifted teacher, as we just heard a little bit from Marika about Chuck himself, and a dedicated mentor to students and younger engineers and faculty. And actually, for a time, Don even came to enjoy the ritualistic end of the workday, which involved a cocktail when he was visiting Chuck in his office in Concord, and work was done, and of course, it was exactly, I believe, at exactly 5 o'clock every day. You had to stop work and have whatever cocktail was being made at that point. The subject of Don's talk tonight, which is on sample disturbance in fine-grained soils, as many of you know, was one of those areas that Chuck had the most intense interest in studying, bringing into practice and writing about. He was most passionate about this topic. And so it's such a wonderful legacy of Chuck's work that Don is going to be talking about that particular topic tonight. The second aspect of Don's career that I want to highlight is the tremendous impact that he's had on the people around him. And I believe this is really the most important part of Don's career is the people that he's impacted. He's been a leader among professional colleagues around the world. Many of you may not know this because Don is so humble and often doesn't talk about this, but has been really all over the world as both a researcher and a practitioner of geotechnical engineering. He's mentored many younger faculty at UMass, as well as other institutions, and they've looked to him for guidance in their careers. You know, in an era when mentoring, to me at least, gets a little bit overused and maybe exaggerated, Don has really served in that role in a substantive way to many, many people. And speaking of mentoring, Don has also educated and mentored 2 generations of geotechnical engineering students at UMass. I know there are many that are here tonight. There's probably many that are listening on Zoom. And I know that he really gave to them the passion for geotechnical engineering through his example and perhaps more importantly, through his own personal qualities. I want to say that Don passed on to many of these students and to many of us these qualities of integrity and diligence, and I know I'm embarrassing him. And as we just saw through Chuck's legacy, his attention to detail and the rewards of hard work and respect for others. And maybe most importantly, maintaining a sense of humor throughout all of it and through life. He's also a dedicated and caring husband and parent. And I don't know if, as we refer to him as #1 son, Ryan is here, but we're hoping he'll join us eventually. And he's also a dedicated and caring friend, unless you try to pass him on a bike or on the Nordic ski track, and then the friendship is basically off because he's also an extremely competitive athlete. So I've been really fortunate to call Don a friend for now some 35 years, and when we met as graduate students, and I'm really gratified and proud to introduce him as the 4th Charles C. Lab Memorial Lecturer tonight. Please join me with a warm welcome for Don.
Thank you, Tom, for that kind introduction. It's a privilege for me to have this opportunity to deliver a lecture in honor of Professor Ladd. And I'm delighted to see many friendly faces from former classmates, students, colleagues, and friends. And as Tom mentioned, I think there are over 100 people on Zoom. And yes, it does include THCA, who's enjoying his breakfast in Bangkok, and CT Chin, apparently in Taipei, is also enjoying his breakfast with Don. So thank you all online for joining us. I picked a topic that was dear to Professor Ladd, and I'm going to jump right into it and present a slide that we actually prepared 20 years ago in preparation for the Casa Grande lecture. Well, actually, Professor Ladd prepared the content. I was the one that knew how to use a computer and prepare a PowerPoint slide. But I felt at the time, this statement at the top about our state of practice has regressed over the years was a bit of a bold statement. And I felt a little bit uncomfortable about that. But of course, Professor Ladd was Professor Ladd. But I found myself, when we were making this presentation to various audiences, having this urge to say, I'm sorry for saying this. And it was only afterwards I realized Canadians apparently say sorry a lot. And so, but now I've had 20 more years of experience then in site characterization through research projects, but perhaps more importantly, through many commercial projects. And for sure, I've worked with many excellent engineers who practice excellent state of the practice site characterization methodologies. But I am sorry to say that there is a lot of examples of poor practice that I came across. And we have to ask ourselves, why is this the case? And we offer 3 reasons here. There are others, but these are 3 reasons we offer. And I think the first one is it's the reality, but it's a bit of a cop-out, because I feel that even if you have to downscale your plans, you can always downscale it to best practice methodologies. I think what's more important is items 2 and 3, and that has to do with education, mentoring, training, and continuing professional development. There are no mysteries to what it takes to do good site investigation practice. It's not a secret. It's not intellectual property. Horslev's book, published in 1949, talks about the value of good quality geometry samplers, mud drilling, rotary sampling, and so forth. And yet we seem to persistently either forget about it or are ignorant about the presence of these best practice methods. So that, by way of background, I decided to split the presentation into 3 parts and actually put sample disturbance in the middle and split site characterization. And the reason I chose to do this is I wanted to first talk about like an overview discussion of what we call integrated site characterization. And within that overview, I want to stress, I guess pun intended, stress history, geologic history, because that was so central to what Professor Ladd was trying to do in developing practical ways of characterizing soils. Then I'll move on to the nitty-gritty details of undisturbed soil sampling. And then I'll wrap up the presentation with a checklist of what we consider to be best practice methods. Now, for sure, there's a lot to be said about the relative role of local experience. I mean, if someone has worked with a particular soil through their career and has been able to calibrate it versus performance monitoring and so forth, there's a lot to be said for just relying on that experience and, let's say, empirical correlations to make it work. I'm sure there are many people in this room here, if we give them a plot of land in the city of Boston, they know exactly what kind of foundation will work for that project. But that doesn't apply to everybody. And that knowledge may not distill down to the younger generation working within that company or in parallel companies for sure. And then certainly it may not necessarily be applicable to new sites. So my target audience really is the younger generation here. I think my generation, we're stuck. We either do best practice methods, or we're stuck in our ways. I mean, how many times have you worked with a driller that said, well, that's the way we've been doing it for 20 years. Doesn't make it right, but that's the way they've been doing it for 20 years. And, surely some of the things that we talk about, the focus really is on more moderate to high value, high risk projects. So what is integrated site characterization? It goes beyond site investigation. It really is a methodology where you try to use a framework to guide you through all of the steps to make the actual site investigation part most efficient. And my friend and colleague, Jason DeYoung, has a paper he's published that listed down there in 2016 that has a framework and a roadmap that describes in detail what integrated site characterization is. But a key component to that roadmap is to develop a priori a geologic model of your anticipated site conditions. And certainly on larger value or higher risk projects, you're going to need to bring in a team of geo experts. And I will show you a case study where that needed to be done. And ideally, it's an iterative process. Now, again, clearly on smaller projects, we're going to build a new Tim Horton Donuts on Route 1 in Saugus. We're going there one day. We only have that amount of time for drilling and sampling. We're not going to apply a lot of the things I'm going to talk about here. We know it's going to work in that case. Now, in the offshore world, where I do a lot of my work, there are two products that come out of an integrated site characterization. One is the ground model. And the ground model is a database of all information collected from the project, both qualitative, usually geologic-based information, and quantitative, things that we like to measure, in situ testing, laboratory testing, and so forth. And ideally, at least in more recent times, this is all being integrated into a GIS type of framework where you can start to use visualization tools and basically allow everyone involved in the project to get access to that data. Once the ground model has been established, we then move on to create the design basis. And that is where we take all the data from the ground model, we do our best interpretations, and we produce design profiles. Usually they're statistical based, so it's best estimate, best upper estimate, best lower estimate. And this is the package that comes out of the integrated site characterization that goes to the designer. Now, in some projects, that person is the same person who did the site investigation, did the desk study and everything. But there are certainly bigger, more challenging and more interesting projects. And offshore wind will be a good one that I'll use as an example in this lecture, where you cannot do it on your own. It is simply impossible. And you need a team of experts to put the whole package together. And again, it all starts with geology. And I have two quotes here from two of the early textbooks of geotechnical engineering. Professor Taylor at MIT, in his book, the quote there you can see talks about the importance of geologic features. And then the rival with Harvard, Terzaghi, produced his book in the same year, not coincidentally. And yet there's a couple of key statements in there that are very telling. Number one is the first step. The first thing you should do is don't call a driller, don't book the driller, but study, do your due diligence in terms of the desk study. Again, frankly, in the greater Boston area, we know it quite well. I'm talking about sites that you either don't have experience with or new regions that you're working on. And what's also very important in the last sentence highlighted in blue is that this is a sentence written in the future tense. So in other words, work with the geology, understand it as best you can before you lay out your site exploration. And the idea here is that when you go to the site, it evolves into a process of more confirmation as opposed to new discovery. And so that you're really confirming what you suspect should be there in terms of developing your site characterization. Now, of course, geology is really interesting in the New England area. since we've been glaciated. And this slide from Janet Stone of USGS in Connecticut shows the extent of the glacial maximal period about 25,000 years ago. And I think many of us are familiar with the fact that the glaciers ended here towards the section where it created Long Island, Block Island, Martha's Vineyard, and Nantucket. And that was basically the terminal moraine. And the fact that our region has been glaciated created a significant influence on the type of soils that have been deposited in the region. And they vary significantly across the state, and likewise in other regions of the world that have been glaciated. So we have a map here on the left, and we know, of course, in our area right here today, we have the marine clay, Boston blue clay was deposited. We have marine clays that have been deposited going up the coast with increasing sensitivity as we go north. Yet you go inland, UMass Amherst is right here. We have Glacial Lake Hitchcock, which was a very long lake, lacustrine lake environment, and that's where our varve clays were deposited. Completely different material than Boston blue clay. And then once again, we have Lake Champlain up here, which was a marine environment where we have deposition of the very sensitive Leda clays. And these can all be explained through the great work that geologists have done in terms of mapping the state and creating maps that we can use so that when we do a site investigation program, we can go to this geologic information first to help us better understand our exploration. But of course, there can be subtle changes in the characteristics of the soil over very small spatial distances. This is a picture of UMass Amherst. At the time when the glaciers were retreating north and they were upwards towards Quebec, the water was about 77 meters deep on top of present-day Amherst. And within that, the sediments were coming in and created the varve clays. The coarser material settled out in the summer, and then when the lake was frozen in the winter, we got the finer grained clay materials, and that was a varve. And we have 1,400 varves on our campus, over 100-foot deposit, so 1,400 years of deposition. But we have on our campus what is supposedly the tallest library in the world. I don't know why you'd want to have the tallest library in the world, but we have it. 26 floors, reinforced concrete, pretty significant dead loads. You fill this thing up with books, which is what they did when it opened. That's a lot of load. And yet this building is on a very simple mat foundation. It's because the campus is basically a drumlin with some sand and gravel on top of glacial till, on top of bedrock. Pretty easy foundation design. You go 400 yards to the west. Right here is the edge of Glacial Lake Hitchcock. And that's where the varve clays were deposited. And the lake bed dipped very steeply into the bowl that was essentially the Connecticut River Valley. And right here is our sports arena, our hockey rink, and it's a equivalent two-story building. It's open structure. The loads are nothing other than when you have 10,000 people in there, but that's still nothing compared to a 26-story library. And yet this is on a deep foundation, Haley and Aldrich project. It's on PIFs, or Frankie piles as we used to call them. And that's because it's in the soft varve clay. And if you look at the geologic maps of this region, it will tell you, you have sand and gravel over here, you have a varve clay over here. And if you design some of these buildings here, this is our new, all our universities are competing on Taj Mahals of fitness centers for students. Well, this is our Taj Mahal, and it's on a shallow foundation. And if you did that building and you then got the project for this building and you said, well, we know what's there, you're of course obviously going to be in big trouble. So that brings me to what Professor Ladd always said, stress history. I like to put geology in parentheses, stress or geologic history. And I think Professor Ladd had great intuition in selecting one of the more famous acronyms in geotechnical engineering, with SHANSEP. I mean, how many times have any of us actually written out what SHANSEP stands for? Probably never. Stress history and normalized soil engineering parameters. It incorporates the two most important aspects of fine-grained soil behavior: the influence of stress history on that behavior, and the fact that you can normalize data. And I'm not talking about whether SHANSEP is applicable or not, but just the concept of normalizing data is so valuable to understanding whether things like your undrained shear strength make any sense for the stress history that your soil has. And if we look at stress history, there are a number of pre-consolidation mechanisms that can cause a soil to be altered from its original depositional environment, and I'll list those in the next slide. But I will say you will rarely encounter a truly normally consolidated soil. I mean, I've had cases where I've worked on projects where people have said, oh my God, we have an under-consolidated soil, which makes no sense at all, because they collected lousy samples, they got pre-consolidation stress below the in situ vertical effective stress. It was just poor quality work. Now, We are geotechnical engineers. At least I personally often struggle working with geologists because they're very qualitative. They use a lot of words that I don't often understand. We like to quantify things. So for us, we take that geologic history, we quantify it. For sands, we use relative density. For clays, we use pre-consolidation stress or the vertical yield stress. So what are some of the things that can cause a soil to change its fundamental behavior characteristics over time? These are the four major categories here. Some of them are obvious. Erosion. One of the best examples is the city of London. A couple of 100 meters of soil has eroded from where present day London is. I mean, that's just like, wow, that's amazing in terms of the geologic history of the city of London. So they have a very stiff, highly over-consolidated clay. Desiccation. We struggle a lot in New England with desiccation. In other parts of the world, we do have a fairly high water table, but it does fluctuate up and down. And we did have ground freezing before vegetation came back after the glaciers. And then we have drain creep, aging, and physiochemical phenomena. But you can see it in the data we get from site exploration programs. These are two CRS curves, vertical strain, log vertical stress, city of Boston. There's a sample from 28 feet, and there's a sample from 71 feet. Completely different 1D compression behavior. The upper one has been desiccated over its geologic history. It changed completely from what the characteristics are of the soil below the desiccated zone. The lower one has not been subjected to any desiccation. It has aged. That mechanism will always be there. And it probably has some physiochemical cementation into it to give a compression curve like that. And that's all at one site, just that difference in depth apart. In fact, there are other even more compelling examples. If we move north to Newberry, Mass, which we still call Boston blue clay, I'm not quite sure if that's actually right or not, but we call it Boston blue clay. And these are CRS tests from 3 samples we collected there that are 2 meters apart in depth in the same borehole. So this far apart, 3 samples. And the data are plotted in this framework that Skempton originally developed, and then Berlin took it up, and then Chandler worked on it. It essentially tries to partition where soils plot in a map of void index, which is just sort of a normalized version of void ratio, versus log stress, and identify with respect to essentially a line that represents the remolded behavior of the soil, and a sedimentation compression line that's more or less the normally consolidated line for the soil. And it's a useful tool. It doesn't solve all our problems, but in this case, it really does work quite well in looking at the differences between these 3 CRS tests. So here we are at 4.3 meters, and the green dot is the in situ vertical effective stress. So we have a very stiff response, and then it starts to curve over a little bit and follows here. We go 1 meter deeper. Our next sample, we run a CRS test here, and we start to get a pretty different stress strain response. And not surprisingly, it eventually merges with this one here. And then 1 more meter deep, we get this one here, very high void ratio, pretty dramatic change at the vertical yield stress, and then starts to again merge with these 2 other curves over here. This is a significant gradient in the pre-consolidation stress. And obviously, if you're doing site characterization work at this site, decisions between shallow foundation and deep foundations clearly need to identify such a gradient. As an aside, what has been an interesting exercise is actually trying to determine the pre-consolidation stress. As many of you know, we have at least a dozen different methods that people have proposed, which is kind of crazy. This is a unique soil property. Why do we have so many different methods? Butterfield, strain energy, Onishi. I mean, it just goes on. And it's because we're trying to do something that is not available in the data that we're trying to analyze. If you have a poor quality sample, you're not going to have any good evidence of yield. If you have stiff clays, you don't have good evidence of yield, even if you have a perfect quality sample. And likewise with silts. And as a little exercise in this, you don't need any method to know that that's the vertical yield stress there, that's the vertical yield stress there. Here, I would give this to myself and students, and you do a Casagrande construction, you'll get a number. I mean, you take a straight line and you put in semi-log space, you'll get a Casagrande construction number. And if I actually take this data and replot it in linear space, once again, vertical yield, perfectly straight line, yet that's what Casagrande would give you as a pre-consolidation stress. So it's an artifact of our graphical construction. Now, if you're doing settlement calculations, in spite of it not being the most satisfying way to do it, it'll work because you take the right slopes, You bifurcate it at that pre-consolidation stress, it'll work. But if you're starting to use normalized soil parameters, you need to be very careful in terms of this. And so we always present our CRS data linear scale first, and then semi-log scale second in terms of presenting the results. And my colleague Alan Lutenayer came up with this little phrase here, estimating sigma prime P a certain uncertainty. And certainly for some soils, I think that's a good phrase. Now, Professor Ladd was also very keen on anisotropy because a lot of his work was associated with stability problems. And this plot shows the interrelationship between stress history and anisotropy. And you may not be able to see a lot of the data points here, but at NGI, we built a database of 30 sites worldwide, mostly offshore sites, where we had samples that were collected. And on each sample, we conducted a strength test and right next to it, a CRS test. So we had pairs. And what are plotted here, traxal compression, DSS, traxal extension, and these were all so-called recompression tests. They were consolidated to the best estimate of the in situ vertical effective stress state, and they were screened for sample quality. We only kept the samples that were in the first 2 quality ratings out of 4, which I'll show you that quality rating later on. And what we see is a very distinct relationship between the undrained shear strength and the pre-consolidation stress, which is the x-axis in these. And in fact, if you just do a simple linear regression, which I'm not saying that's what the data should be represented by, but you do it, you get these coefficients of 0.28, 0.22, and 0.17. And that's, of course, anisotropy, the influence of the major principal stress on the undrained shear strength that you will measure, something Professor Ladd was very passionate about. Now, we could further refine this data, which we did, bringing plasticity into the picture. And as many of you know, lower plasticity soils, which we have a lot around here, are highly anisotropic. But the point remains that we have to consider the fact that the first thing that is influencing these soils is their stress history. Then the second thing that's influencing them is the orientation of the major principal stress that we are imposing on those soils based on what we're building. And some of you may be interested to know that if you just take the average of these, you get Professor Mesri's 0.22 sigma prime P. So by that as a way of background, I'm trying to make the point that knowing stress history is so critical to doing a good site characterization program. Now, when we jump into the fields, we use in situ testing and we use laboratory testing. And there are pros and cons to both. You may ask the question, why do we have so many in situ tests out there? And I will be somewhat exaggerating, somewhat facetious to say, it's because none of them measure what we want. You want more circle. You want the failure envelope. None of these devices can do that. They measure soil behavior response. In order to get what we want, which is friction angle and undrained shear strength, we have to go through empirical correlations. And some of them are good, and some of them are lousy, and some of them have pretty widespread in them. But in situ testing can be very efficient and very fast, especially for spatial variability, particularly the piezo cone test that I'm going to talk about quite a bit further on. On the other end of the spectrum, we have what I call the lab testing enterprise. And it takes a lot to get a sample from the ground into the lab. It can go through a lot depending on what we do to it. So through all of these stages, things can go wrong that will continuously degrade the quality of that sample, especially for softer clays. And so in the part on sample disturbance, I'm going to go through all of these steps and talk about the various factors that control what we're looking for. On the other hand, we have a sample. We're in the lab. We have controlled boundary conditions. We can control stresses. We control drainage. We control strain rate. We can measure what we want. Traxal test, we get more circle. We can measure the undrained shear strength, do a CRS test, get the vertical yield stress. But none of that data is particularly useful unless we have good quality samples. So we have this challenge balancing the best of both worlds. And when I get to the third part of the talk, I'll give at least some of our recommendations on what we consider would be best practice methods. But as a bit of a preview, I have a quote here from Professor Peck, who very nicely says, if you have a fairly well-defined soil profile, it merits doing good quality drilling and sampling and getting the exact characteristics of that soil that you would like to measure directly in the laboratory. On the other hand, if you have a highly heterogeneous profile with ill-defined layers, which I can say a lot of the coastal plain where we're doing offshore development right now for wind, we have a lot of that there, then you need to be a lot more careful about how much you're going to put into the lab testing program. You need to lean a lot more on the in situ testing program, which we do in the offshore wind sector, but we don't necessarily do it for this. We do it for economic reasons, again, as I'll show later. Well, in fact, I'll start now with I'll wrap up this part of the talk with a little bit of an example project. This is called the Dogger Bank Offshore Wind Zone. And it is a lease area in the North Sea. It is to this day still the largest lease area that has been awarded. If all of the sections of the lease are developed, it'll amount to over 6 gigawatts of energy. And the wind turbines keep getting bigger, so that number will likely keep going up. And the reason they picked Dogger Bank is that it is a bank. It's a fishing bank. It's an area of fairly shallow water. And when you're talking about monopiles as the foundation for offshore wind turbines, shallow water is good. But little did they know what they were getting into. And just for spatial scale, there's the city of London. That's the size of the Dogger Bank offshore wind farm. And a consortium of energy companies were put together. Statoil is now called Equinor, and the Crown Estate was leading all of this effort, and it was called Forewind. And early on in the project, there's a big project, big spatial scale, going to do an integrated study. First thing you look to is the geology. So British Geological Society was brought on board, and this was their geologic map of that region of the North Sea. It's like a fence diagram. And basically there's Dogger Bank, 1 unit. It's like, cool, just 1 unit, suggests homogeneous, suggests no challenges, pretty boring for the geologist actually, good for the engineers, maybe not as challenging, but should be pretty straightforward. But of course, history tells us that this was not always water. There was land connection between the UK and Europe, and there's the Dogger Bank zone. And now you're starting to think, okay, wait a second, this wasn't underwater all the time. There was a big glacier that came through the UK. There was a big glacier that came from Scandinavia. Turns out they met basically at Dogger Bank. You start thinking, okay, we might not have a nice uniform soil profile here. It might be a bit more complicated. And sure enough, some of the early data started to come in and said, wow, there's a lot of heterogeneity in this project. And so the geo team leader, Turing Eshelta of Equinor Statoil, in my estimation, one of the best offshore geotechnical engineers in the world, period. He was the team leader, and he quickly recognized that he needed to put a comprehensive team together to really do a proper job of characterizing his site. I mean, there are billions of dollars on the line here. So he literally brought in from different companies, experts in site investigation, lab testing, in situ testing, geophysical, geostatisticians, and so forth, and essentially had quarterly meetings where he locked the team in a room and said, you're not coming out until you make sense of this latest round of data that has come in. Now, obviously, there was a great opportunity to do iterative. So the site investigation program happened over multiple years. And the slide I'm showing here is what led up to what's called the consent phase. And the consent phase is simply you need to prepare a package to convince the federal government or the UK government that you have the capability to continue working and eventually develop this wind farm. So the SI work did not stop here. But look at the data that was collected, 60,000 line kilometers of geophysical data. I mean, this was terabytes of data. And thank God we had geophysicists on the project, because every time I look at one of those things, I have no idea what I'm looking at. I mean, I see lines going this way and that way, and they're very valuable, but they don't give us numbers. We want numbers. But look at the geotech part. 7 kilometers of CPTU profiles were collected. That's a lot of data to look at. 70 boreholes in the offshore world market, about 15 to 30% of each turbine location will have a borehole. All the rest will be CPTs, sometimes multiple CPTs. And then hundreds of so-called advanced laboratory tests, CRS, CAU, DSS, and CAUC. And again, I want to stress this was only 2014. The work consent was approved. There's been another 8 years of work, and these numbers have easily doubled and tripled. This is an enormous amount of data coming in, impossible to make sense of this as an individual. Also, very difficult to make sense of this in siloed teams with different companies. I mean, the brilliance of Turing is he forced the teams to work together. He even brought some of the designers in who were waiting down the road for our final project so that they can interact with us and help us focus on what's important and more important. And what was a really interesting experience is that while we were working on the project, again, there's our geologic map, we found the glacial geologists started using our CPT data to start figuring out the geologic history. And I remember Tom Loon and I looking at each other and saying, wait a second, it's supposed to be the other way around. They're supposed to give us the geologic history to help us make sense of our data. But again, because it was an integrated team, it came together very nicely. And geoscientists are great at making cartoons, and this was the updated cartoon map that now replaces this one here. I mean, you had everything here. The glaciers colliding. Some of the glaciers had a so-called wet interface that smoothly rode over the till. Some had a dry interface that caused glacial thrusting and faulting in the soil. This you can see in the geophysical mapping. We had in channels, sometimes filled with soft clay, sometimes filled with North Sea sand, which that was the easiest part to characterize, just ordinary quartz sand from the North Sea. But the most significant thing was that we eventually were able to get the geologists to confirm that this place was airly exposed for many tens of thousands of years. And that causes desiccation, deep freezing, and lowering a water table. And as those of you know, they've worked with desiccated soils, they are very, very difficult to characterize. The data is usually all over the place. And when the early data, lab data started coming in, I started looking at the CRS data. It made no sense whatsoever. The word desiccation had not yet come up, and I look at it and I'm thinking, wow, this looks like a desiccated soil. And that became a central focus of going forward and trying to help us make sense of the data to eventually come up with a design basis. And that design basis was the CPT data were tuned to every single geologic unit at this site. And some of them, we had enough data to be confident. Others, it was pushing it a little bit. But for the main thick, stiff clay deposit at this site that is heavily desiccated, the lab wasn't going to do it. There was just too much scattering the data. And so Torringa was clever enough to be able to do large-scale field testing. Rented a jack-up barge, jacked up the barge, took the data from the barge feet as a foundation failure. The Met mast for Met Ocean data, analyzed that, it was a suction bucket caisson, and used that to tune the CPT data in order to correlate towards undrained shear strength and pre-consolidation stress. Closer to home here, we, as some of you know, have an exponentially growing offshore wind industry in the Northeast. And I will just say, good luck finding a drilling vessel over the next few years, and good luck finding a lab that does good quality testing and has the capacity to take on this work. The rest of the world is not stopping, and yet we're coming on board, and this is a lot of work. These things are spatially enormous, the landmass involved. Now, one of the interesting things we have here, of course, is the previous slide I showed, the glacial maximum. These hatched areas are some of the lease areas that have already been awarded. And frankly, I would not have bid on a lease area that sits right here because that's where the terminal moraine is. And it's loaded with cobbles and boulders. And this figure here, which you can't see very well, it's about 5 meters across, 5 meters up. This is from Frugo's investigation of the South Warwick Wind Farm, which used to be Deepwater Wind. Now it's Ørsted, right there. All those little dots are boulders and cobbles. There are thousands of them. And those are expressed at the seabed. Then you go through cross sections, you have many more. So you can imagine the challenges presents with installing the foundations, but also the cable routes going to shore. There's a very high probability that any of these leases beyond this glacial maximum do not have these cobbles and boulders, which some of them can be the size of a house, I've been told. And so far, the data coming in from some of these sites are proving that to be the case. What is also interesting is we have a lot of glauconite, and I never heard of the word glauconite until 3 years ago. And this is a very interesting material. It presents as a granular material. And as you shear it, it turns into a clay. If you take the undisturbed material, you can do a grain size on it. You mix it up, you can do Atterberg limits on it. And this is causing a lot of worry because it starts to gum up pile driving. And my colleague at UMass Amherst, Zach Westgate, is currently leading a joint industry project funded by Ørsted and Equinor, driving piles into glauconite in the state of New Jersey, which has a lot of glauconite. And they're really worried about being able to drive the piles in. They're not worried about capacity. It's about driving them in. These vessels are hundreds of thousands of dollars a day. And if you don't mobilize the right equipment, you're talking about a really serious problem. So these are some really fascinating challenges. And I think some really nice work. It's not too often we get to work with a new material that we don't know much about. And so I think it's an exciting opportunity. And then finally, this is the latest round of leases that were let by BOEM. This was about a month ago, $4.4 billion for 6 leases. This is just to have the opportunity to consider developing the site. Just here's your money, take it and you don't get it back. Now, unfortunately, this money goes into the black hole of Washington. None of it is earmarked to feed back into the industry, but the amount of money here is just incredible. And they will be spending untold amount of money doing the site characterization work for these. And there are many more in the pipeline. And then now coastal California is getting in the picture, and so is South Carolina, and so is Florida, and so is Texas. There is a ton of work coming forward in this industry, and I think it's very exciting, especially for the younger generation here in the audience. Okay, so that's the end of part one. Now I want to do a deep dive into Professor Ladd's first love, which is sampling and sample disturbance. And we're going to start by looking at a stress path. And I know this may cause a little bit of PTSD for some of you, but we have to use stress paths because they are so valuable. And the question asked is, we have a low OCR clay. We know K-naught's less than 1, so it's sitting here in PQ space at 0.1 here. And if we come along, let's say, and load it in a vertical direction, we know we develop positive shear-induced pore pressures, and we get some undrained shear strength. We collect a sample, we bring it back to the lab, and we find out that the effective stress in the sample is over here. How do we know that? Well, we can actually measure the suction because the pore pressures goes negative when we have a suction. And in the old days, you would do this in a Traxel cell with a null indicator. And if you know what a null indicator is, you should be retired by now. But we have more modern, sorry, Jack, you don't need to retire. You look so young anyway, so you're good. You're good for another 20 years. But we also have suction probes that can actually measure the negative pore water pressure in the soil. And this was one of Professor Ladd's first piece of research work. It was his first major paper in the 1960s with Lamb, which was the effective stress after sampling. And if you do a really good state-of-the-art job of collecting a soil sample, you will still lose about 70% of the vertical effective stress in the sample. And if you do a lousy job, you'll be down to almost 100% loss. And so we have this sample sitting here. It's at an isotropic state of stress, which has nothing to do with in situ. It now has a huge OCR, which has nothing to do with in situ. We don't actually know what the effective stress is, but let's do a UU test anyways, because it's inexpensive, quick, and we'll get a number. And of course, the stress path now will go to the right. It'll exhibit dilated behavior because it's a high OCR specimen now. And so one of the points Professor Ladd tried so hard to stress is that the behavior here has absolutely nothing to do with the in situ behavior. So you better, if you're going to use it, have really rock solid correlations to use that data and a depth of experience that gives you the confidence to do that. But let's ask the question, how did we get here? So the first step is we have to drill a borehole, and we cannot avoid that. There's going to be stress relief. But the interesting thing is that when we drill a borehole, it's like a Traxel extension test. So even if we have a drilling mud, we're going to get a reduction in the vertical stress. We start to migrate over Traxel extension. We cross the Q axis, which Professor Ladd called the perfect sampling, just as a frame of reference for his work. And then if you keep going, and if you do a lousy job, you don't use a drilling mud, you could actually fail a soil that you want to sample in extension unloading before you actually collect the sample. So the first job is to stay as far away from this failure envelope as possible. We cannot avoid this process up to point 2, but we don't want to go to point D here, where we've actually created failure before we even run the test. The next step, which Professor Bali worked on, and CT Chin, who's listening in, did his work on this, is, well, what happens when you push a tube into the soil? And in Professor Bali's work, which is strain path method, he found that the soil, so the soil is here waiting to be sampled, the tube is coming along, the soil goes through a compression cycle, reverses to an extension cycle, and then more or less returns back to where it started. So it's one cyclic loop back and forth. And in his research, he found that when you look at the geometries of samplers, thicker samplers and so forth, that induced larger strains. We go to our stress path here. So we go through a compression path. Now our stress path is migrating a little bit to the right because now we're over consolidated. Go to the extension, go to the compression, we're over here. We continuously migrate to the left because these are all shearing actions, and low OCR clays develop positive shear-induced pore pressures. So we're losing effective stress continuously. And as you know, the Varves clays are a great example. So there's an SPT sample of a weighted rod Varve clay, and you can see the significant distortions in the Varves. It's an SPT sample, so we're not expecting a good sample, but it's just a very good visual reminder. On the other hand, on the right here, an X-ray done for us by Dr. Germain, you can see our Varves are perfectly straight all the way to the edge of the tube, and this is a fixed piston sample. So finishing the stress path, Marika. back to Marika, you're over there, back to Professor Ladd. So of course he did all this by hand when we were working on the Casagrande paper. He has his name, he has all the dates here and everything. And there's the full stress path. And he needed someone to take his hand drawings and put it in a computer drawing. So that was moi with respect to my drafting background. And so now we have this figure and we were at 0.5. The tube is in the ground. There's a lot of suction to get that tube out of the ground. It's a sealed environment. Get the suction in the ground. You get a little bit of water content redistribution from the edges to the perimeter. Then you extrude the tube in the lab. You do a little bit of trimming and boom, we're at 0.9. So the soil has gone through a lot. And the question is, well, what's the consequence of this? And so what people have worked on, a number of organizations and ourselves included, is to do research where you try different methods, you try different sampling techniques. And one of the things I learned early on in my career is that it's always good to do something you know is going to be lousy. At first I thought, why do something lousy? But then I realized that's a nice data point on the other extreme to show your good data by contrast. So we did some work in Newbury, Mass, where we did an SPT sample in a hollow stem auger hole with no mud. We did a hollow stem auger hole with a standard Shelby tube with a free piston, not locked, but just a free piston. Then we did mud rotary, which of course is best practice. We used a somewhat modified Shelby tube. I'll show you that later. And then we did what's considered the state of the art, which is Sherbrooke block sampler. This has been proven to be able to collect the best quality samples. So that's our frame of reference. If you don't know what a Sherbrooke block sampler looks like, this is our block sampler here. It has 3 tubes that inject water. The blades are open. You can use it with a regular drill rig. This is just a CME 55 rig. And you rotate, you slowly carve an annulus, and then you activate the under blades to provide basal support, and you pull the block out of the ground. And there's your block sample, and you seal it up, and you're ready to bring it to the lab. And that can be used as your reference behavior in the lab. So what are some of the things that people measure? Here are CRS curves for soil from that Newbury site. And the green curve is the block sample. So what I like to say, very nice looking compression curve. What's really nice to see is that the fixed piston sample with a somewhat modified geometry and a mudded borehole gave essentially the same behavior as a Sherbrooke block sample. When we went to a non-mudded borehole, we started to lose signature characteristics of the behavior of the soil. And then we went with the lousy piston sampler, or sorry, SPT sampler. We pretty much lost all of the characteristics. And you can see that more distinctly here with linear scales in this plot. In terms of undrained shear strength, it can be a little bit trickier because with undrained shear strength, especially when we run consolidated tests, we are now reconsolidating the sample. So if we have a pretty lousy sample, we might get a lot of consolidation strains, and that's going to change things. So you have destructurization, they're kind of working against each other. But these are samples we collected at the Onsøy test site in Norway. They have a thick walled 54 millimeter sampler. That was our lousy sampler. A pretty good fixed piston and a Sherbrooke block sampler. You can see the stress strain curves. You can see the stress paths here. And I think it's fair to say for some projects, people might say, well, so what? There's not a big difference. Well, I can tell you for projects Professor Ladd worked on, this is a pretty important difference in terms of whether you need to stage construction or not. And it actually brings me to a little segue about this word conservative. I think, at least as academics, we do a poor job of giving students the impression of what conservative means. I think they think it means low. Go low and you'll be good. Well, there are a lot of design applications, especially in the offshore world, suction buckets for anchoring offshore oil and gas platforms, and now floating offshore wind turbines are using suction buckets. You need to get the undrained shear strength profile very tight because you got to be able to install the suction bucket, but then you have to have it perform under service loading. And now also with monopiles. And this is a typical this is an old picture now, and these monopiles are up to 10 meters in diameter now. You got to make sure that the contractor knows exactly what kind of equipment they need to mobilize to get that in the ground. And then you need to make sure it has enough capacity. So you can't go low on one end and high on the other end and say, well, it's conservative, I'm going to be good. And again, in the offshore world, if you mobilize the wrong vessel, that's a lot of money. That's hundreds of thousands of dollars a day. So I just, my rant here is we just be a little bit conservative about, okay, what the word conservative means. Well, Professor Ladd worked a lot on clays. What about what we call intermediate soils, which are this dirty subject we don't talk about in undergraduate soil mechanics. We go clay, we go sand, and we skip everything in between other than classification. They are complicated. These are traxel compression tests run on a young PI equal to 4 silt. Young means we reconstitute in the laboratory. OCR 1.8. The black one is the specimen consolidated, sheared, undrained. And we get contractive behavior. Loops over to the failure envelope here. We then applied a Bally strain cycle to the blue sample. It was plus or minus 0.5% strain cycle. These are 70 millimeter specimens. 0.5% is less than half a millimeter displacement. Consolidated back to the same effective stress state, and we get completely different stress strain behavior. A little bit of contracted behavior, and then switch to dilative and starts to ride up the failure envelope. Then when we apply a plus or minus 3% strain cycle, we get something totally different. Loops up, rides along the failure envelope. And the key point here is that when you collect a sample of these soils, you don't know what the disposition of your sample is. You don't know how loose or dense it is in the ground unless you have really good in situ data. You just have a sample, and you measure this behavior versus this behavior. That's obviously significant consequence, except for drain problems. Doesn't affect the friction angle. So P prime is the same for everything. So I guess that's a good outcome. Oops, wrong direction. We also went to the Halden silt site in Norway, and we used that NGI 15 millimeter sampler, a gel push sampler, and again, the Sherbrooke block sampler. And this is a silt. Here's another one of the crazy things about our profession. It's 89% silt. The Casa Grande PI is 2. If you do the fall cone PI, you get 8. Some of you know there are differences in the way we measure the liquid limit around the world, which is kind of like nuts, but that is what it is. But I can tell you, whenever you have a soil that has less than about 5%, 5 to 10% clay, PI less than 2, you can't trim it. It's going to liquefy on you. This is about the border. We just were barely able to collect and trim these samples. And now there's our Sherbrooke block sample, dilative behavior. There's the gel push sampler, and there's the 54 millimeter sampler, completely different stress strain characteristics. Now they all follow the same failure envelope, so that's good for drained analysis, but for undrained, depending on what strain levels you need to concern yourself with, there's a significant difference in the behavioral response that you're obtaining here. A few years ago, Jason DeYoung and myself went back to the site and brought our gust sampler. It's an Acker gust sampler. And we got the stress strain curve. We actually got the gust sampler and shipped the samples back to Amherst, ran the test, and we were quite pleased to see that in this material, we can also get very good quality samples using a fixed piston type of sampler with respect to the approach that was used. And finally, one last example for stiff high OCR clays. The really interesting thing about this is that the sampling effective stress is now a completely different picture than soft clay. Soft clays were always great. It's always going lower, lower, and lower. Stiff clays, it can go the other way because the shearing process, because it's a very stiff high OCR clay, is now developing negative shear induced pore pressures. You can have an effective stress in your sample sitting on the bench under zero total stress that has a higher effective stress than it is in the ground. And so we start to see things like this, where the UU test, which Professor Ladd really hammered against, and I will repeat that in a foregoing slide, has a higher undrained shear strength than the so-called high quality CAU-C test. In fact, when you run CAU-C test, you got to be very careful to watch for swelling during reconsolidation. That's a big challenge with these materials. And even more interesting, we collected this data at an offshore site. We measured sensitivity with the UU test, and we got sensitivities less than 1, a lot of them less than 1. And you're thinking, that's not possible. Well, this is a site where the soil was desiccated. You can kind of guess which site it is. It has a lot of macro and micro features. And so the intact samples had these, planes of weakness. But perhaps more significantly, this soil is really hard to remold. I mean, the soil in plastic bags, using hammers to try and remold it, a lot of additional shearing, effective stress keeps going up, and you can get the remolded sample having a higher undrained shear strength than the intact sample. So initially caused a lot of confusion, but we were able to figure it out and explain it through basic soil mechanics. So it's not always you get a low value on disturbed samples, I guess my point is. So how do we quantify sample quality? Well, we don't have a definitive method. We don't have like you poke the sample and it says I'm good, and then you go run your test. But we have some very useful tools. And one of them is X-raying. I think Dr. Germain produces the best X-rays in the world. These are 4 examples, although I'll say in the offshore world, we now use CAT scans. Spending more money on a CAT scan than I get on my body when I have to go to the hospital on an offshore sample. I mean, Zach Westgate was just talking about a project we're working on, $10,000 to get CAT scans for a handful of samples, but that's the offshore world. In any event, in these Shelby tubes, white is a void, clearly disturbed sample. The rock is not necessarily a problem per se, could have been a drop stone. Heavily disturbed sample. These are pretty obvious even to a good tech when they're extruded. This is a more concern. These are more subtle signatures of disturbance, curvature at the edges, little cracks, and then you see a nice quality fixed piston sample of the Varv clay, lines all the way to the edge. This is a great first step, but we are engineers. We like to quantify things. And so NGI, particularly Tom Luna, spent a lot of time and effort developing a sample quality rating criteria that essentially says how much volumetric strain does it take to get that soil back to where it was in the ground. And clearly the more strain, the worse things you did to it. And so they've kind of iterated through the process over the years and have come up with this final framework. And the red line essentially means if you're above the red line, you can be pretty confident that you can rely on the data for design. You're below the red line, you need to rethink about what you're doing. The problem is we've seen people apply this to soils that are not part of this restriction. I've seen people apply it to soils that have a higher OCR because they don't even report the OCR in their report. And they were testing stiff clays and they were getting almost no strain. In fact, they were getting swelling in some cases. And I thought, wow, look, we got great quality samples. Really example of poor practice. And people are applying this to silts, which are very stiff on 1D loading, and it's certainly not applicable. So to that end, Jason DeYoung worked towards trying to use a strain energy-based approach that uses the unload reload loop, and it is applicable to both clays and intermediate soils. But the holy grail is to try and come up with something that is actually non-destructive. In everything I've described to you so far, you have to run the test to find out what the quality of your sample was. So you get the information afterwards. Oh, by the way, an example, again, back to Newberry, Boston blue clay, pre-consolidation stress versus delta URE knot, block samples, good quality fixed piston sample, poor quality piston or poor quality tube sample, and then the SPT samples. I mean, the trend is very distinct. So David Height came up with a method, a non-destructive method for evaluating samples using shear wave velocity and sample suction. And the idea behind this framework is that the soil has some inherent backbone curve in terms of the shear wave velocity versus the product of the stress. And shear wave velocity depends on the stress product. So if you can measure the in situ shear wave velocity, seismic piezo cone, if you can estimate the in situ stress, we can always do sigma V, we got to find a K naught to do sigma H. You can develop a backbone curve for the soil. And then when you come along and take your sample, at least for low OCR clays, we are always going to migrate to the left from the in situ state, migrate down. And of course, our worst quality sample would be something where the shear wave is very low and the suction is very low. And a bunch of us working in soft clays, UC Dublin, NGI, ourselves, thought, let's try this out for soft clays. Another challenge is we've been trying to work on it with intermediate soils like silts, but there you have to somehow quantify for the potential for the samples to have contracted or dilated during sampling. And that's a whole nother level of complexity. But applying this method, you can build bender elements. These are just little piezo ceramic elements. You can put them in simple platens. You can take a cut section of a Shelby tube, run a shear wave velocity across it, or Melissa Landon here is doing some of her PhD research on a block sample in Onsoy, again, measuring shear wave velocity across there. It's not a particularly difficult test to run, but it's not the most friendly test to run in the field where things are messy and there's a lot of environmental conditions. On the suction side, Steve Poirier, who I think is in the audience here somewhere, hey, Steve, he developed in parallel to Melissa the suction probe. And the suction probe is a more modern day version of measuring the negative pore water pressure in the sample. And the goal was to build something that had off-the-shelf parts, a pressure transducer, a housing, a high bar air entry stone, and most critically, a copper seal that's the size of a wedding ring. And if Jack Germain had not told me to use a copper seal, I don't know if Steve would have ever graduated. Rubber O-rings do not hold suction. And when we introduced this copper ring, we could get negative pore water pressures down to the megapascal range without cavitation. You got to saturate it properly. And yet we didn't need to go anywhere near that. In the London clay, they need such high numbers because it's so stiff. We were more in the 100 type of KPA range. But thanks so much, Jack. You really saved us on that one. Or you saved Steve, actually, and my guilt, I suppose. So what did the data look like? Here is shear wave velocity measured actually in the field on our samples, normalized by, we ran seismic piezo cone tests versus delta E naught. And you know, it's a nice looking trend. It is 3 soils. That's not a lot, but it is 3 soils. Suction has a bit of a more challenge to measure because the release of suction depends so much on the grain size characteristics of the soil. Not as much with shear wave velocity. It's much more dependent on the stress state. And so we definitely see a trend here, but we definitely see some greater variability in the trend. The big challenge we have is that when we try to put it in David Height's framework, his framework works where you're measuring suctions in and around the effective stress because they're stiff soils. We're all the way over here at very low suctions. And so you have to do a significant extrapolation of the backbone curve. And that's really tenuous. So this is still a work in progress, trying to couple these measurements with these measurements in order to come up with this a priori non-destructive way of measuring sample disturbance. Now, what do we do about remediation? There's 2 issues to consider. If we've had constrained swelling, which is basically redistribution of water content in a tube, that's not a big deal. We can reconsolidate in situ stresses. But if we've had shear distortions that have destructurized the physiochemical bonds, that's a big problem. You can't make them come back. That would be wishful thinking. And so you have a few choices in terms of what to do, in terms of reconsolidation options. You could do nothing, which is very common and popular in practice. You just take the sample as is and you run a shear test. A UU, a Torr vane, a pocket pen, fall cone, lab vane, we've got a whole bunch of them. Or you can do what NGI developed, which is let's bring the soil back to the in situ stress state, because that's what we want to measure the behavior at. Now we know we've had some sample disturbance, so we're going to get a little bit of volumetric change. And the idea was if we collected a pretty good sample, we balance them out. Professor Ladd took a totally different approach insofar as he did not have confidence in the quality of a lot of samples that were collected. And then he went and relied on stress history and normalized soil engineering parameters and said, let's bring the soil to states that are well-defined, measure the soil and the normalized soil engineering parameters, and then apply your best job at determining the stress history of the site to get your design parameters. Otherwise, the methods are completely identical in terms of what they advocate with respect to the testing regime. So back to the UU test. If you use UU test for measuring, let's say SCU average for stability problems, as Dr. Germain and Professor Ladd showed, you could be, it's like the 3 bears eating the oatmeal. You know, one was a little too hot, one was a little too cold, and one was just right. It happens. You showed this in your case studies. The problem is you don't know where you are. You don't know which bear you are. That's the big challenge, unless you are really good at analyzing the data with respect to normalized parameters and so forth. And the reasons of concern are that, number one, we have an effective stress state that has nothing to do with in situ, and we don't know what it is because we don't measure suction in routine practice. We're running triaxial compression, so SU is too high there for SU average. We're shearing fast, so SU is too high there. We have excessive sample disturbance, SU is too low. They're compensating errors, but you never know to what degree they're compensating. So it's a moving target. And as a result of that, you often get profiles that look like this. If the thing goes backwards, there we go. There's a project Professor Ladd worked on, UU test, Torr vane test. There's a project I worked on, a stiff offshore clay. These are UU tests. Good luck picking a design basis for both of these. I mean, you couldn't get a better plot with a shotgun in terms of the variability of data. And again, I want to emphasize over here, you can say, wow, let's, you know, I want to sleep at night. Let's just do this. Well, you have a real problem with the pile drivability analysis. So it's not that simple, just going low. Okay, so now to the last part, sort of a bullet list of practical best practice recommendations. And I believe very strongly it all starts with companies having very detailed method statements. This is very common in the offshore industry, less common on land. I've seen some companies like David Height's company does a very good job of this. In the offshore world, Ørsted does a phenomenal job of this. And what they are documents that detail exactly what you want, step by step, detail by detail for everything. Drilling, sampling, in situ testing, lab data, reporting, all of that stuff. Because you need to clear up all of these potential misunderstandings that happen. Because a lot of times, in sort of the unfortunate nature of our business, that a lot of companies no longer have in-house drilling, have in-house lab. So now you're going across companies. Now you're the client. And yeah, there are good drillers. There are good labs. But the communication in terms of what you need done is so important. And it's not enough just to reference an ASTM standard, which, by the way, I want to shout out Richard, Jack, and Amy for all the work you've done in ASTM over the years. We owe the three of you a huge debt of gratitude. And so I think companies need to develop these and find your in-house experts. And if you don't have in-house experts, bring in some peer experts, bring in some experts and have them help you develop these method statements. And they need to be constantly updated. The standards are constantly evolving. We're writing a new version of the Marine Soil Investigation Standard right now, and it's changed quite a bit from the previous one. It's all applicable to renewables and so forth. And you need to be on top of this. So I can't stress this point enough. So how do we approach the site characterization practice? Well, as I also already said before, it's all about geology, but don't drill boreholes everywhere. Be very selective with your boreholes. Just make sure they're done properly using the methods I'm going to suggest are such in some of the forthcoming slides. Lean more on spatially distributed in situ tests. It's all about the piezo cone, and try as best as possible to develop soil or site-specific correlations between the lab and the in situ data. Does anyone recognize this handsome young gentleman over here? Professor Ladd, supervising a drilling crew in Venezuela. I keep pressing the back button. Sorry, go forward. So drilling, it's all about mud rotary. You want to collect a good quality undisturbed sample of a fine grained soil, you need to do mud rotary drilling. Just throw the hollow stem augers out. Don't let them use it. So many companies got into the environmental drilling, which hollow stem augers work well for monitoring wells, then got into the geotechnical drilling. Don't let them use it. You need to pay very close attention to what the driller is doing with respect to weight of the mud, the discharge bit. We like to use the bigger diameter NW rods because they give a better concentric boring operation. And you need to be especially careful when all the rods come out because they can sling 20, 30, 40 feet of rods and they can pull them out quick and your mud level drops quickly. And then you get the stress relief you don't want. Again, this is not new. This is all fairly well-known information, yet time and again, I see it not being applied in practice. Thin-walled Shelby tube. Of course, the perfect tube has no wall thickness, but that's impossible. So some parameters that research have shown is that the area ratio, which is basically the area of the OD to the ID, should be less than 10%. The standard off-the-shelf US Shelby tube is about 11%. You need to have an inside clearance ratio of 0. The standard US Shelby tube does not have 0. There's a relief. And the idea there is you don't want the specimen swelling once it goes into the tube. And the standard US Shelby tube does not have a sharp cutting angle. It's bent in. If you ever use a pipe cutter, it looks like a pipe cutter. Cut it. I now believe, and so we for years used a 5-degree cutting angle, but it is really sharp. And frankly, it is dangerous. And it is delicate. And you know, as some of you know, in Boston Blue Clay, we have these drop stones. You hit one of those, it's going to bend it, and then you're done. So I have moved away. I'm more in the 15 to 20 degree range. I think it's a secondary factor. The reason I know that is we've tested a lot of regular Shelby tubes, and we've gotten good quality samples. I think the most important factor is to use a fixed piston sampler, which, I mean, you and Ladd said that way back when we were working in the Arctic work. They didn't use a fixed piston sampler, got lousy samples. Jack went up there with a fixed piston sampler, got good quality samples. But again, you'd be surprised at how many people are challenged to do this. Now, a fixed piston sampler can be rod actuated, or it can be hydraulically actuated. We have an Acker Gus sampler. That's this one over here. The rod actuated one is not easy to use. I've worked with drill rigs in Europe where they're specifically tooled to handle the double rods, but most of the rigs here are not, and it can be a real mess. So most drillers use the Gus sampler. A couple of things, key things about the Gus sampler is that the packers, which look exactly like this, need to be in good condition and properly hydrated. That's critical. So whenever I go sampling with the Gus sampler, I put them in a Shelby tube and I put them in a bucket of water and I leave it there overnight. I've had a number of calls of people saying, oh, we used the Gus sampler and it's a piece of crap that came up empty. It's because they didn't take care of the packers. Can I say crap in Northeastern, Tom? Yeah, okay, thanks, yeah. The other thing is, The other thing is there are several O-ring seals in the gust sampler. And when you're testing a silty material, that silt gets in the O-ring seals and you're going to run in trouble. So when we do gust sampling, I just take the whole thing apart every time. It takes about 10 minutes and I repack the rings and I pack the packers. And we actually, this is in Halden, Norway. We collected 7 + 6, 14 fixed piston samples down to 20 meters depth, 24-inch recovery on all of them. Doesn't mean we collected a perfect sample, but it's a step in the right direction. It can be a challenge to get the piston head out of the sample. The gust sampler actually has a little mechanism that you can rotate. I haven't had much luck with that. But about 25 years ago, one of my grad students said, why don't we just drill a hole? And I was like, duh, yeah, of course. So we just drill a hole right in front of the piston head, and that's our suction relief to get the piston out of the sample. With respect to in situ testing, it really is all about the piezo cone. And yet there are a lot of things in practice that are not done very well. And especially important one is poor saturation. Fortunately, in the offshore world, we don't have to worry about that. The water, especially in deeper water, it back pressures the whole system. So not a problem. But as you develop time and experience with your company or through publications, you can start to develop plots like this, which is again, Newberry, Mass. The green symbols are CRS tests, pre-consolidation stress values. This is our CPT profile, and I didn't calibrate the two. I just picked 1/3. That's sort of the average relationship between sigma prime P and 1/3 Q naught. Now I could tune this for the site, but I would be very confident in estimating what the pre-consolidation stress is with depth here. So my point is, as you gain experience interlinking these two tools, you can start to be more efficient in reducing the lab side, which I don't know why I'm saying that because I'm primarily a lab person, but that is the reality of it. With respect to transport and storage, this is generally not a problem unless people really do egregious things with your samples. You put them in the back of your car. These are some fixed piston samples we collected. They are buckled in more safely than my kids were when they were children. We do seal our samples, especially our block samples, with a 50-50 mix of wax and petroleum jelly. It's much more ductile than ordinary wax. It's waterproof, airproof. I can't tell you how many tubes have come in our lab covered in wax and the stuff just falls all off. But it's especially important for our block samples. And as an example of transport, these are CRS curves for block samples of the Lita clay that we sampled up in Ottawa. Liquidity index, my batteries run out. Liquidity index of 3. And we drove up there in a small van, collected the block samples, sealed them up, drove back. I had nightmares that they were just going to be all over the back of the van, having liquefied essentially. And there's the CRS curve we got at UMass Amherst. So transport is not that big a problem for clays. Silts is a different story, but for clays. A couple of other examples. These are block samples we collected in Norway, at Onsøy site. The black curves, we opened the blocks at NGI. We did CRS test. We sealed the rest of the block. We went to the airport, said a prayer, put it on a commercial airline, got them in Amherst the following summer, did the CRS test, and you can see the comparison. So this was very satisfying to see. So again, I think transport, unless something catastrophic happens, I know in some cases you can put min-max thermometers, you can put little accelerometers in there to see if they've popped, meaning something has dropped in terms of the transport process. Storage. We do seal our important samples in this 50-50 mix. And Arash Pirazzi, who's I think on Moodle, one of my former PhD students, we ran a CRS test on a sample that we've had since 2003. My wife complains I don't throw anything away. Well, this is the reason I don't throw anything away. So 14 years apart, and the blue curve versus the gray curve. So you can store samples. We are currently working on Shelby tubes that have been stored for a long time. That's probably a little bit more dicey, but we're going to see what happens. But we will for sure be debonding those tubes. When we process the tubes, we never use anything within about 1 to 1.5 diameters to the bottom. My standard procedures, if it's a full tube, I go up 4 inches, I cut, and I start from there. The bottom part, Atterberg limits, grain size, or whatever. And we debond using the wire, which is what Jack Tremaine developed. One of his many excellent contributions to our profession, to debond the soil. So we cut with a saw for clay soils. If it has a very low PI and it's silty, can't use the saw. We use a pipe cutter. If it is almost non-plastic, there's nothing you can do. You won't get the sample out without liquefying it. And then you call the engineer and say, what do you want to do? In terms of advanced laboratory testing, it's all about the CRS. It's all about stress history, which again, I think is what Professor Ladd was trying to stress. We always go first to the CRS. I've worked on many projects at NGI, and that's the first test we specify, even for projects where we don't even care about settlement. We want to know what the pre-consolidation stress is. That allows us to better plan the more expensive, more time-consuming advanced laboratory test program. It allows us to pick our stresses and allows us to make sense of the data in terms of normalized soil parameters. You got to make a decision of recompression versus SHANSEP. I could talk for hours about our experiences with these two, but Tom is getting nervous. It's getting close to his bedtime, so I need to move on. But there are some obvious pros and cons of both. But what I will say is that in the SHANSEP method, Professor Ladd explicitly required you to assess the stress history. It is essential to the method. You should never produce recompression data without also explicitly evaluating the stress history and evaluating the data in the context of that stress history. The SHANSEP equation perfectly fits recompression data just as it does SHANSEP data. Now, the nice thing about how things have evolved over the years is equipment. We have tremendous developments compared to when we all started to what you can do now. And picture on the left is Professor Ladd doing what he does best, being very careful, being very diligent, and writing everything down. The middle picture, however, Richard Ladd, a little bit more of a rebel, also saying, what the heck, it's a SHANSEP test. Who cares? Let's just bang this thing and get it over with. You see the mercury pots in the back there. I remember when I was a student, we'd see these little beads of mercury rolling along the floor. I said, well, that's cold. But then I think maybe that's not such a good thing. Automated equipment really has improved the testing world tremendously. And it's a huge development. And to get totally nerdy, which drives Tom crazy, is, I just love seeing data like this. This is a SHANSEP test on one of the Gloucester Leda clays. That on the left is a one-dimensional compression curve under K-naught consolidation. Perfect compression curve in terms of stress history, the yield stress, the slopes, and then we get the undrained shear strength behavior of the soil at the end of the test. And again, what's very valuable is to develop a body of experience on typical values that you can use in, I'll call it the SHANSEP equation, but again, it's applicable to recompression tests and other measurements of soil behavior. And so we offer some typical S values and M values that you can use. Certainly appropriate for preliminary design, maybe low risk projects, but always should be used to evaluate your data and build your database. Keep collecting more experience with these variables. We have a whole collection of data of similar parameters for Boston Blue Clay, for example, from commercial projects. And finally, I'm going to end on a couple of slides that give an example of poor practice. This is a project in the greater Boston area, very thick deposit of Boston Blue Clay. And what did they do? They went out with SPT, which sorry, but really a waste of time and money. Yeah, you got to wait a rod. Okay, that's no big surprise. It's perfect for CPT in this case. I know CPT is a bit more expensive. You got to get Cone Tech out of New Jersey, 10,000 to mobilize, maybe another 7,000 to 10,000 daily rate. But you got to think about the overall big picture of your project that can be very cost effective. You look at the pre-consolidation stress values from the odometer test. Big red flag there, as you can see, obviously. Undrained shear strength profile data plotted like this doesn't really tell you anything, other than there's quite a bit of scatter. What you need to do, of course, is, although in this case you really didn't need to do it, but you can evaluate the sample quality. The data is already there. You get it when you run the test. You can see the delta ERE values on the left plot. All the ones in red are below that red border line I showed you. Unreliable data, not surprising. They're the ones that plot below the pre-consolidation stress. Secondly, you look at the undrained shear strength, always reference data to profiles of like 0.1 and 0.3 sigma prime V naught. No soil will have an undrained shear strength less than 10% of the vertical effective stress. Just not going to happen. Those data were clearly collected on disturbed tubes, and we got low values in this case for a soft clay. It happens to be, we eventually went back to this site, when we first saw this data. We did a piezo cone profile, and just using not even site-specific values of S&M got what we would consider to be a pragmatic approach to evaluating the stress history, showing it's normally consolidated depth. I know it's not, it's undergone some aging, but it's a pragmatic choice. And then developing an undrained shear strength profile that now falls in between the 0.1 and 0.3 bands, which is reasonable for a low OCR soil. So some takeaway points. When it comes to characterizing soft clays, I've said it several times, the CPT is an excellent tool. Evaluation of stress history is essential. I think I've said it enough. It's what Professor Ladd always advocated, and I'm still strongly trying to advocate it today. Number three, there are no mysteries here. We know what to do. Many people do it this way, but there are enough out there that is still of great concern. And of even greater concern, some people are just not yet aware of these issues. And it's a question of education, which falls on us to start with. The professors at the universities that start educating our younger generations. And then the great value of using normalized soil parameters. I have one slide on continuing challenge, which is what we call intermediate soils. The questions being, will your soil behave clay-like or will it behave silt-like? Depends on the PI, depends on the silt fraction. And that's a tough decision. More sand-like, lean on in situ testing more. More clay-like, you can get samples and do the testing. The boundary has not been perfectly well defined. If you have a soil that is fairly loose, I'm not sure if that's the right word to use for silts, but it's going to exhibit contracted behavior, and you don't do a very good job sampling, you are pretty much guaranteed to measure dilated behavior in the lab, and that's a big problem. If you do legitimately have dilated behavior, as shown by the stress path here on the right, and you have to analyze for undrained problems such as rapid loading, offshore mud mats, pile installation, cyclic loading, you need to think hard about what is going to be my undrained shear strength. Where are you going to be along this curve for the undrained shear strength you're going to use for design? And clearly on the pile driving side, you're going to go further up, to be conservative, to use a word I said don't use. Whereas on the stability side, you're going to come lower down. The good thing is, as I said before, if it's a drain problem, friction angle is going to be fine. Disturbance doesn't seem to affect the friction angle. Okay, that's the end of my talk. A lot of the tenets that I described today, Jason DeYoung and I wrote in this paper. And if you have a chance to read the paper, we would love to hear from you. We would like to hear of things we haven't thought of or been exposed to, things you may disagree with, or things that you agree with. It would be great to hear from you. So to wrap up, allow me a few minutes to say some words of thanks. I've had the great privilege of working with many engineers over my career, and I'm extremely grateful for that. But it all starts with a person who I fondly call the control tower, which is my partner in life, Virginia. We met in 1980 as civil engineering undergraduates in a class of 55 students, 3 females, and somehow this shy, insecure, nerdy engineer got one of them. Miracles happen. And when I was doing my doctorate at MIT, Carol Ladd, Professor Ladd's wife, took Virginia aside one day and said, Virginia, if you want Don to graduate, you need to get pregnant. And I think Carol was speaking from deep experience. And somehow Virginia tricked me into getting pregnant. And so our PhD child, Carolina, was born, and that did indeed force me to focus on graduating. And then when I joined UMass Amherst and I was on the tenure track, which was probably even more intense than trying to finish my PhD, Virginia tricked me again. And, kicked me in the ass and said, here's another kid that you need to worry about. And so number one son, who is sitting here somewhere, was born. And to put it in geotechnical engineering terms, because of my training, I'm a soft clay person. Virginia is the bedrock of our family. Professors Ladd and Germain, what a privilege it had been to be educated, trained, mentored. You got my career off to a great start, and nothing makes me more pleased and proud to be able to call you colleagues and lifelong friends. Such dedication and such outstanding knowledge about soil behavior and laboratory experimentation and so forth. And I will say, if Jack Germain was not in the lab at MIT helping me develop my equipment, It doesn't matter how many kids Virginia had, I would have never graduated. And Marika, your presentation was awesome because I wanted to create some PTSD for those of us in here who have worked with Professor Ladd. I keep everything fantastic, Marika. Now Virginia is not going to complain about me keeping everything. I still have all of my handwritten notes from Professor Ladd for my dissertation. And this page that you can't read here, this is my chapter 5 of my thesis, the chapter, presentation, interpretation, and results. And you can't quite read this, but when I got the package from Ladd, I ran back to my office. I was just like anxious. And when I read the first sentence, it says, magnificent data and magnificent presentation that I thoroughly enjoyed going through. And I was like, yes. And then I thought, this feels pretty thick. This feels a lot thicker than what I gave him. Like it feels twice as thick as what I gave him. And as Marika showed, his ability to focus and comment and improve your work is just amazing. Tom Sheehan, we have followed parallel careers. We met in the lab at MIT. Professor Ladd and Jermaine were our advisors. We followed an academic career path. We've worked on many projects, wrote many papers. Tom is by far the best technical and fastest writer I've ever worked with. I have many times sent him my part of something to write and I get a reply and said, DeGroot, what is this brain fart you sent me? But he's really good at editing it. We served as mutual psychiatrists, free charge psychiatrists in managing our career. This was the day before cell phones and email. So it was on the phone. Tom, what's your worry? Or Don, what's your worry? And we would help each other out. Our wife said, you guys talk more than you talk to us. And in fact, one day, the UMass admin person came to me with my phone bill and said, boy, you make a lot of calls and receive a lot of calls from the 617 area code. But as some of you know, Tom has climbed the academic administrative ladder at Northeastern. In fact, Tom is in the C-suite now at Northeastern University. I can't get a hold of him. I have to talk to his people. I don't have people, it's me. And I can't get through to him, but I think he's grown a little bored of me talking about Atterberg limits and all of these things, and just doesn't have the time for me. But I couldn't ask for a better best friend. At BBF, there you go, better best friend. Thank you so much, Tom. In terms of site characterization, I learned a lot when I went to UMass Amherst from Al Lutnager. Al has an endless stream of ideas. He also has exceptional mechanical aptitude. I mean, how many professors build their own piezo cone equipment and their own frame to use the piezo cone equipment? And I'm very grateful to Al for that. And then Jason DeYoung was at UMass Amherst for a few years before he defected to UC Davis. And again, I enjoyed working with Jason. He's not afraid to take on great challenges, and we still work together to this day. I like this picture because, as some of you know, we're both of Dutch descent. And de Jong means the young one, which it's self-evident if you look at the picture who the young one is. But I occasionally have to remind him that the group means the great one. So as George Costanza said, at least I got that going for me. Lucy Jen, thank you so much for everything you do for the Ladd Lecture and the Ladd Fund. It's just, as I learned in Boston, it's wicked awesome what you do for the fund. The middle of the picture, standing next to Professor Ladd, Suzanne Lacoste. I wanted to do my first sabbatical at NGI in 1997, and I started communicating with Suzanne through letters and so forth. And she would ask me, who do you want to work with? And I just wanted to go there. I just wanted to hang out. I mean, it's NGI. And little did I realize that NGI, while still doing high-end research, was a major international consulting operation, to over 200 employees, people on billable hours and so forth. And just saying, I just want to hang out is not a very good plan. And you have to find someone that was willing to take the extra time and effort to work with you, be your host, so to speak. And one of Suzanne's many talents is she can really read people. And she partnered me with Tom Luna. And I'm so grateful to Suzanne for that. That was transformative in my career and in my life professionally. Because ever since 1997, Tom Luna and I have been working together on projects. And in that first year, 97, we worked on a project for Touring a Shelter on the left here, Stado at the time, Equinor now. And he's a close personal friend to Tom. And these are two outstanding engineers. And I am so grateful to have had the opportunity to work with them. And then my last slide, graduate students. I apologize if you're here and your picture's not here. It's a random collection. Sometimes they drove me nuts. It's like having kids at home, kids at work. But there's nothing more important in our job than training, mentoring, and educating graduate students. And I'm grateful for that opportunity. Thank you.
Thank you, Don. That was an amazing presentation. Chuck Ladd would be extremely proud of what you had to say. Hopefully the profession is going to take some of this to heart and we're going to see some improvements. So I'd like to open the floor to questions for Don, not questions for me. So anybody like to step up? We have we have two people with microphones down here, George. Just a minute, Richard.
Right here.
Okay.
I'd like to point out a couple things. I do have not really a technical question, but I'd like to point out to the crowd that it was a great lecture. And Tom keyed on a few things that I loved so much about my brother, and also lab testing. My whole career was spent just on the testing side. And I can appreciate as many things that you said, and I totally believe in. Like you take NGI. When I first started working at MIT, Lawrence Burham came over from NGI, and he taught us about things that they were doing over there and evaluated and talked about some stuff. And I was the flunky. I'd pick him up at the airport and bring him and stuff. And NGI had a great approach. I mean, you've followed, I went to NGI a couple times and I've devoted with them, and your philosophy about what they have to teach us and everything is right on. And I appreciate that. And then also, from a family point of view, when my brother died, Don was at the funeral and made the presentation on the professional side. And it was a great job. And it meant a lot to the family. I hope to keep coming every other year until it's my time to get out of here. But it was a great lecture. And one of the points that I loved about it is the emphasis on the SHANSEP approach. I followed in my brother's footsteps and used that and was able to really help the profession in the lab testing, using and applying the SHANSEP approach that you solve a lot of problems by using normalized behavior and working with those parameters. And in that, I followed a lot of the things like you pointed out about Jack. So great job.
Thank you, Richard. Anybody else? No questions? There we go. I would.
So Don, you showed some really interesting data in there. I just was fascinated by one piece of data you showed from Newbury. I don't know if you could put the slide up just to entertain me.
Can we go back to the presentation slides?
It's the one very early on where you had the three
yeah,
from 3 1 meter
Yep.
interval.
I'm not sure.
I'm not sure they can go back, but maybe you can ask a
Okay.
question.
Well, could be. I don't think I've ever seen such a large gradient
Yep.
of change of properties in such a short depth range from high quality data. And Newbury's not that far away. Jack and I spent a lot of time out at Saugus, as you
Yep.
probably recall. It's not very far north. What is the reason for this? Is there anything else you can tell us that's specific that would explain that contrast over such a short interval?
The quick answer is I'm really not sure. It's a bit of a cop-out.
Load 'em up.
It's possible there's some kind of, I don't think that's going to work, some kind of cementation in that upper material. But I have to lean on my colleague Guoping Zhang to figure that out for me eventually. But we were focused on the lower material. And so we didn't pay much attention to the upper material, but we were trying to work out our block sampling protocol. So we had the samples, and then eventually we tested. And it was only 2 years ago we published that data. But yeah, the gradient is phenomenal. But the piezo cone picks it up really well. So I'm sorry, that's not a very good answer, but it's
I'm just intrigued.
Yeah.
I mean, you said something before also. You said we're all familiar with Boston blue clay, and I was thinking, yeah, I thought so. And,
well, the thing that's really interesting is the crust in Boston is very deep. The crust here is very shallow. And also the clay gets more sensitive as you go north. The sensitivity of depth here is about 20 at this site. And that probably is some kind of cementation to the soil. Yeah, it's very interesting. Yeah.
Anybody else? No?
Yes.
Wait a minute, Matt. We have people online, so you do.
All right, makes sense. So why do you think there's such a variation in measured shear strength in desiccated clays?
Tough question. The nature of desiccation, especially when it's from drying, happens at such a small micro scale in terms of developing those large suction stresses that cause the soil to contract upon itself. And I think that varies tremendously on a very, very small spatial scale. I think that's one big reason. The second reason is you get micro and macro features that are somewhat randomly distributed. I mean, London clay has some very distinct fissures, but there's a pretty systematic pattern to it because it was unloading passive failure type of phenomena. But in a desiccated clay, every single one I've worked with, it's all over the place. You really cannot characterize a desiccated clay in a very systematic way. It's a big challenge. And Professor Ladd said, don't use the SHANSEP method for desiccated clays. And then it becomes the engineer making a pragmatic decision on where you're going to go with your undrained shear strength. And in the Dogger Bank offshore wind farm, it consumed a few years of our effort because we had to come up with a design basis. And in the end, we had to go to scale, not full scale, but large scale field testing, which they did in the London clay with plate load test. But again, the London clay was a bit more understandable with the fracture pattern. But we do, unfortunately, I couldn't share the data because it's not public domain yet, but we have tuned in on a set of recommendations for the CPT based on those large scale field tests. And that's what we've put in the design basis. But we were nowhere near that before those field tests were taking place.
Thank you.
Oh, and yeah, we have a question up the back.
Yep.
Don, thank you. It's a great talk. As just Richard said, I'm Guoping Zhang. I'm Don's colleague at UMass. Actually, after today's the talk, I realized I didn't know you before at all. For the past 8 years, you infused me a lot of new knowledge, actually. Although I've taken...
We work together all the time in the lab.
but there are a lot of new things to me, actually. I took Professor Ladd's soil behavior 3 times. Anyway, a technical question here is about sample storage. What do you think the influence of thixotropy? Will that affect soil behavior a little bit, or strength or stiffness? Thank you. The technical question.
Should I mention Deirdre O'Neill?
Sure.
I think it depends how much the soil has undergone in terms of shearing during the whole sampling process, which is, by definition, thixotropy is you break down the soil and then over time it starts to regain its strength. But the results I showed were from a Sherbrooke block sample, which presumably did not go under anywhere near the level of destructurization that happens in poor quality samples. So I think it didn't have the opportunity or the need to develop a thixotropic gain. If you had a poor quality sample, it will presumably gain some strength over time. I mean, we've seen that time and again in the work we've done together on thixotropic hardening. But I think in that case, it didn't play a role. My classmate, Deirdre O'Neill, spent a lot of time trying to figure out why resedimented Boston blue clay got stronger with time, and thixotropy was one thing she looked at. But I think bugs was another hypothesis. So again, in summary, I don't think in those samples thixotropy is playing a role.
Okay, thank you. Let me just get thank you, everybody. So we have a couple more orders of business to take care of before we let you go. It's an absolute pleasure to welcome Don as the 4th member of the Charles C. Ladd Memorial Lecture Series. And for that, we have these awards of appreciation, which you can see the picture of here, which is something that actually Lucy Jen developed the whole concept and managed to pull all of the pieces together in order to make these extremely impressive acrylic pieces. And those of you who followed Chuck's career know that he basically did the bulk of his research on 6 specific clays. And Lucy was able to acquire all 6 of those clays, which is Boston blue clay, Leda clay, Atchafalaya clay, Maine Presumpscot clay, Connecticut Valley Varved clay, and San Francisco Bay mud. So we acquired samples from each of those, cut little cubes, dried those out, and embedded them in the acrylic. And these are one of a kind, which it has the Charles C. Memorial Lecture at the top. It's an award of appreciation presented to Professor Don J. DeGroot for his lecture, Causes, Effects, and you can't read these things very well, folks, and Mitigation of Sample Disturbance of Fine-Grained Soils. Hard to read, harder to take pictures of. And it is absolutely a pleasure to turn this over to you, sir. Great lecture.
It's a pleasure to receive it.
All right, very good. And with that, I'd like to ask John Erickson to join us, and he's going to present something else, which I don't know where it went. Oh, awesome.
Oh, you can do whatever you want. Good evening, everyone. My name is John Erickson, and on behalf of the GI, I'd like to thank both Professor DeGroot for a fantastic lecture, and I'd also like to thank all of you for attending tonight. You know, obviously the last few years have been difficult for events like this, so it's extremely exciting for us all to be together, and I hope tonight is a sign of things to come for a return to normalcy. Before I extend my thanks to those who made tonight possible, on a personal note, I would like to take a moment to thank Don for his tutelage and guidance to myself and so many of us here tonight. I was lucky enough to study under Professor DeGroot and the rest of the amazing staff at UMass Amherst, and I can't say enough not only about Don's effective teaching style and just the way he served as a teacher, mentor, and a wealth of knowledge to all of his students. Most impressive to me was the way that Professor DeGroot demystified the lab, and he made so many aspects of geotechnical testing and engineering seem very approachable. Using the foundational knowledge we had learned in the classroom, Professor DeGroot was able to so clearly teach the whys and hows of lab testing, in addition to just the procedures, which to me is one of the hallmarks of a truly great professor. And, you know, even more than just his knowledge, he was just always a very easy person to approach, talk hockey with, which as a Bruins fan was a lot more fun when I was in school. And, you know, frankly, he's just a great all around guy. Yeah, it turns out wearing a Canadians t-shirt to your test is no substitute for studying a little bit more, but so, you know, although I never got to meet Professor Ladd personally, looking around tonight and knowing all the UMass students who have established themselves here in Boston in the geotechnical field, and all of those who are, you know, watching remotely now, I really can't think of a better way to honor the legacy of one of our most celebrated professors than to recognize how one of his own students has taught and inspired a whole new generation of geotechnical engineers. So, Don, on behalf of all of us, thank you so much. I would now like to present 2 tokens of our appreciation. First, as was previously mentioned, we have the 2nd generation, or the new and improved Ladd mugs featuring the embankment sketch. I would like to thank everybody, both Professor Ladd's students and the donors who made this possible and coordinated the creation of these mugs. So we've got 2 of them in there for you.
Great, thank you so much.
Absolutely, and secondly, oh yeah, this is a big one. I would like to present Don with the perpetual plaque for the Ladd Lecture to memorialize his participation in this amazing event and tradition.
Wow, thank you so much, John.
In closing, I would like to extend a special thanks to everybody who made tonight possible, namely, you know, the Gang of 6. Oh, I don't know you all by memory. They were going to be on the next slide. I'd like to thank the Gang 6, Professor DeGroot, Professor Lou Edgers, Professor Jack Germain, Professor Lucy Jen, Dr. Suzanne Lacoste, and Professor Tom Sheehan. I'd also like to thank Molly Liddell and everybody at Northeastern for letting us have this event. And I'd also like to thank the members of the BSCES GI committee who have been bopping around tonight doing all sorts of different duties. So again, I'd like to thank everybody for being here. I hope you look forward to more events like this instead of Zoom calls. And thank you again, Tom.